Hello students, welcome to lecture 9. In the previous class um, we came to know about the construction and working model of enhancement type MOSFET. We discussed a few steady state characteristics. So in this session we will continue with the steady state characteristics, and we will know the switching characteristics of MOSFET. So by the end of this session, you will be able to describe steady state characteristics and switching characteristics of power MOSFETs. So if you recall, MOSFET, it is a voltage control device. So there is at the gate terminal, we apply some voltage which will cause the device or the MOSFET to conduct, right? So we clearly understood the working of the enhancement type MOSFET, where initially uh, there would have been no channel uh, where the current would flow, but due to the voltage applied at the across gate and source terminals, there was enhancement of the channel taking place. Okay, so because of the inversion process, due to which there is a channel formed between drain and source, and the current would flow from um, a source to drain, right? So we observed the working there in the previous class. So the actually the gate draws very small leakage current there in the order of nanoamperes. So if we talk about the specifications or the current gain, we know generally the current gain is measured in terms of the output current to input current, right? So here in terms of MOSFET, it would have been drain current versus input current, that is uh, uh, input gate current, that is IG, which would have been in order of 10 to the power of 9, all right? But here, since we know that the gate draws very small leakage current, this current gain is not of important parameter. While in MOSFETs, transconductance is the important parameter which we have to look at, where transconductance is the ratio of the drain current to gate voltage. So this transfer characteristics for N channel and P channel MOSFETs is shown in this figure, where you can see this is the plot of drain current, that is output current, with respect to input voltage, that is voltage across gate and source. All right. So if you observe here, when we discussed enhancement type MOSFET, that is N channel enhancement type MOSFET, at VGS is equal to 0, there would have been no drain current. But as we increase VGS more than the threshold voltage, that is after threshold voltage, there would be significant increase of the drain current. Okay, so this is the typical transfer characteristics of the MOSFET, as you can observe there. So we also discussed the output characteristics, which is depicted in this uh, in the figure. So the output characteristics, we observed that there were three regions of operation. The cutoff region, where we saw if VGS is less than VT, then there would have been no drain current, or drain current would be 0. Then the second region is the pinch off region or the saturation region, where we saw the VDS, if it is greater than or equal to VGS minus VT, then we said that it was pinch off region or the saturation region. And if you recall, that would have been the condition where there would be pinching off, and that is the pinching off of the width of the channel across drain terminal, and that is where the uh, drain current would reach saturation or become almost constant, right? So that is our saturation region or the pinch off region. Then linear region, as you can observe from the dotted lines there. So the linear region is where VDS is less than or equal to VGS minus VT. Okay, VDS is less than or equal to VGS minus VT. So this is the region where the drain current would be in proportion with the VDS, that is drain to source voltage, right? So from these three regions, we observed that cutoff means where the switch would be or the device would be in turn off condition or switch off condition. Pinch off region or the linear region where it would be, especially if it is in linear region, then the device would be used as turn on condition or switch on condition, right? So in MOSFET, we discussed that MOSFET for switching application, it would have been used in linear region, unlike BJT, which was in saturation region. All right. So yeah, these were the three important three regions of operations which we already discussed in the previous class. And just to remind you, pinch off occurs at VDS equal to VGS minus VT. Okay, so that is where the reduction in the width of the channel take place, and there is a saturation of the drain current. That is pinch off condition. So it is when VDS is equal to VGS minus VT. Okay. So some parameters where we have to observe here and recall. Uh, so as VGS is increased, that is voltage across gate to source is increased more than the threshold voltage. The drain current relation can be given with this nonlinear relationship with respect to gate to source voltage, which is given by ID, which is equal to K times square of VGS minus VT, where your K is the constant, that's a function of construction of the device, which can be again in turn measured from this relation. All right, where ID on and VGS on are the parameters which we can get from the characteristics of the device. Okay, generally it will be available in the data sheets. So as we know, the MOSFET will be used in linear region, which is also called ohmic region. The ID characteristics, that is the relation between the current and voltage, can be given by these two relations. So when for very small values of VDS, that is drain to source voltage, when it is less than the threshold voltage, then the minimum drain current what we can get would be given by this relation. ID is equal to K times square of VGS minus VT. So the steady state model for both the depletion type and the enhancement type is shown in this figure. The steady state model and its equivalent circuit is given here. So from this, the transconductance, it is defined as the change in the drain current to change in the gate to source voltage, that is GM. It is the ratio of drain current to VGS, keeping VDS constant. With VDS keeping constant, the transconductance can be measured from the steady state model. And the output resistance, all these are relations, please note down. The output resistance R0 are also given by RDS. It is defined as, or it is a ratio of VDS by ID. So in pinch off region, this output resistance, typically it is in order of mega ohms, that is in pinch off region, while in a linear region, it is on the order of milliohms. All right. So coming to the switching characteristics, we can clearly understand with this switching model, where if you're not considering any gate signal or the input signal, then the whole setup or the enhancement type MOSFET can be imagined as two diodes connected back to back. So, or as an NPN transistor. So that gate structure, you can imagine, has a parasitic capacitance to source given by CGS and capacitance to the drain as CGD. The NPN transistor has a reverse bias junction from drain to source and offers the capacitance CDS. So if you imagine these uh, three different capacitances in the NPN type of transistor, then you will have the switching model which can be implemented or which can be used to understand the switching waveforms or the times. Okay, so if you imagine at the input you have CGS, that is capacitance CGS, and CGD, gate to source and gate to drain, and across drain to source, if you imagine a capacitance CDS, then you can understand the switching of the device. So the MOSFET is a fastest switching device because it has switching speed fastest compared to BJT or any other device. The switching speed is in terms of nanoseconds. That's why it is mainly used in most of these switching applications because it is fastest. The switching speed is fastest. So if we have to understand the switching waveform, we actually look into the characteristics. That is, we look at the time, turn on time and turn off time, right? So if you recall again, turn on time is the sum of delay and rise time, right? So here, if you observe from this waveform, see this VG is nothing but the voltage what you're applying across the gate terminal. All right. So based on the VGS, voltage across gate and source, that is when you decide how the device is working, right? Based on the condition of the voltage across gate and source terminals, that's how you decide the different regions of operations of the device, right? Cutoff region, pinch off region, or saturation region, or the linear region. So based on this, so that again, it depends on the timings or the different position of this VGS voltage. All right. So let's understand. So turn off means what? I mean, so turn on, it is a summation of this uh, turn on delay plus rise time. So what is this turn on delay time? It is the time required to charge the input capacitance to the threshold voltage level. I hope you are getting. VT is our threshold voltage. So VGS should be greater than VT. Only then there will be a channel getting formed and there will be some path for the current to flow, right? So this turn on delay, TD on, turn on delay time is the time required to charge the input capacitance. Remember the input capacitance? To charge the input capacitance to this threshold voltage, right? And what is this TR, rise time? TR or the rise time is the gate charging time from the threshold level to the full gate voltage, VGSP. Okay. So the time required to charge, that is gate charging time from the threshold level to the full range or the full gate voltage, VGSP. So what is this voltage actually? Which is nothing but the voltage required to drive the transistor into linear region. Understand? The voltage required to drive the transistor to linear region. That is the voltage required. All right. So that total becomes, the summation becomes our turn on time. All right. If you observe turn off condition or the characteristics, in turn off you have delay turn off delay time, TD off, which is the time required for the input capacitance to discharge from override to pinch off region. Okay, observe here. it is the time required for the input capacitance to discharge from override voltage to the pinch off region. That will be your turn off delay time. Okay. And what you have this fall time. This fall time is the time required for the input capacitance to discharge from pinch off region to threshold voltage. Okay, so only after VGS is less than threshold voltage where your the device or the transistor turns off, right? So this turn off time or the fall time is the time required for the input capacitance to discharge from pinch off region to threshold voltage. So only after this, when VGS is below this threshold voltage, the device will turn off. So that is your switching characteristics. So just to summarize again, turn on delay TD on is the time to charge the input capacitance to VT. Rise time TR is the charging time to charge the input capacitance to full gate voltage VGSP in order to drive the transistor to the linear region of operation. And turn off delay time TD off, it is the time for the input capacitance to discharge from overdrive voltage to pinch off region. And fall time is the time for the input capacitance to discharge from pinch off region to threshold voltage. Okay, so that's about the switching characteristics. So that's all about the steady state characteristics and the switching characteristics of MOSFET. All right, so that's all for this session. Please go through the presentation again and again to understand clearly. In order to understand this session, you have to have knowledge of the previous session where we discussed the construction and working of the enhancement type MOSFET. Okay, I hope you're doing so. See you in the next session.